Hi, once again, everybody. Today we're going to talk about the math that we use in learning about biomechanics and kinesiology. In specific, we're going to talk about vector analysis. Now, I promise you, I only use the math to the extent that it really illuminates how it works. It isn't my objective into making you into biomechanists, just physical therapists who understand how big the forces are and where they're coming from, sort of, qualitatively, not exactly. Once you're a clinician, you'll almost never have to calculate joint forces. Hopefully you remember how vectors are represented. First of all, the magnitude of a vector is signified by the length of this arrow here, and the direction of the vector is signified by its direction. So what we're going to be talking about today is resolution mainly, and to some extent addition of vectors in two dimensions. And in order to do that, we're going to have to think about some trigonometry. I'll wait just a moment for your collective groan. In a right triangle, C in this diagram over on the right side of the slide is the hypotenuse, or the longest arm of the right triangle. The other arms of the right triangle are denoted relative to their location to the most acute angle of the triangle, which is called theta in the diagram. So the adjacent is that arm of the right triangle that is adjacent to the angle theta, but not the hypotenuse, and the opposite is that arm of the triangle that is opposite of the angle theta, not touching the angle theta at all. I'd imagine that everybody remembers the Pythagorean theorem of a squared plus b squared equals c squared, c being the hypotenuse. So if you wanted to add two vectors that are orthogonal to each other, orthogonal meaning that their directions don't overlap even a little bit, then you could find the hypotenuse. The hypotenuse c equals the square root of a squared plus b squared. Or if you wanted to if you had the resultant vector, which would be represented by the hypotenuse, and we'll talk more about this over the next few minutes. So your resultant vector is represented by the hypotenuse, but you want to find one of the two-dimensional components, you could do it with a variation of that same equation. So for instance, if you wanted to find, in this case, the vertical component, you could use the equation a squared equals the square root of c squared minus b squared. This is how I recommend you think about sine and cosine when resolving vectors in two dimensions. What you see on this slide is a unit circle. So the hypotenuse is the yellow segment going from the origin of the circle up to the perimeter of the circle. So sine is the vertical component going from the horizontal axis up to where the hypotenuse intersects with the unit circle, and cosine is the horizontal component going from the vertical axis to where the hypotenuse intersects the unit circle. This is really the easiest way to calculate how much of a vector in two dimensions at least is going vertically and how much is going horizontally. When I've described this in the past, a lot of students had exclaimed pretty emphatically that this was not how they learned to do trigonometry. And they look kind of like this. However, you don't really have to despair because they really mean the same thing either way. So what people mostly learned for trigonometry is not this bit with the unit circle, but instead that the sine equals the opposite over the hypotenuse. However, if the hypotenuse in this unit circle example is 1, then the sine is just the opposite, right? So in this unit circle equation, the sine is just the vertical component, same as it was when you consider it a unit circle. In the same way, The cosine is the adjacent over the hypotenuse, but remember that the hypotenuse is 1, so anything divided by 1 is itself. So therefore the cosine is just the adjacent over 1, or the adjacent, and therefore the cosine equals the horizontal component of the unit circle. So you see, it's actually the same either way, so you don't really need to fret. So let us go ahead and resolve a vector for practice. So we're going to find out how to resolve the vector on the left side of the equation into a vertical and horizontal component, right? We're going to consider the example of the quadriceps pulling on the patella. So say that the quadriceps force is 500 newtons. There's a super translatory force, and there's the compressive force, or the horizontal force. Now these are facing different directions, but don't worry about the sign S-I-G-N in this case, because if we wanted it to all be positive, we could just turn the diagram around and it would be the same either way. Anyway, the vertical force, or superior transitory force, is the quadriceps force sine A, and there we see the angle A between the vector and the horizontal axis. So to figure it out, the sine of A is the sine of 50 degrees, or 0.77. So we have the quadriceps force of 500 times 0.77, which equals 385 newtons. The compressive force driving the patella into the intracondylar groove is a quad force of 500 times the cosine of that angle A, which is 50 degrees. So it's 500 newtons, which is quadriceps force, times 0.64, which is the cosine of 50 degrees, which equals 321 newtons. Very simple, very easy, yes? Remember that I only want you to have to do math to the extent that it illuminates things about biomechanics and kinesiology. So vector addition is a procedure where the difficulty of the math really doesn't justify the payoff in understanding of the topic, with the exception of adding vectors that are at a right angle to each other. So I'd like for you to know about it, but you don't need to actually do it over the course of your time with me. So in order to do vector addition, you need to use the law of cosines. And the law of cosines, I will only say this because it's part of the joke, is the square of the length of any side of a triangle is equal to the sum of the squares of the lengths of the other two sides of that triangle minus 2 times the product of the lengths of the other two sides and the cosine of the angle opposite of the original side. If you've ever seen the movie Wizard of Oz, after the Scarecrow gets his THD, Doctor of Thinkology diploma, he says to the wizard, "Oh joy, oh rapture, how can I ever thank you enough?" To which the wizard replies, "Well, you can't." Here is the law of cosines in formula. So here is an example of vector addition being done. Remember, I will not ask you to do this over the next couple of semesters, but it might be worthwhile to know that such an operation exists. So we want to know the summation of the force of the supraspinatus plus the summation of gravity working on the arm. And here is the angle between the two vectors, and here is the length and direction of the resulting vector. So to figure that out, we have the supraspinatus force B, 45 newtons, and the gravity force C of 40 newtons, and the angle between the two being 60 degrees, and the cosine of 60 degrees is 0.5. And here you see the, here you see the formula applied, and here you see the solution. Okay, so the important thing that we have to think about is how vectors can be resolved into orthogonal, meaning no overlapping components through trigonometric analysis, And if you're adding vectors, the vector will be greater in magnitude than any one of the vectors, but smaller than the sum of the two vectors just added together. So that's what you need to remember.